Functions, really, the whole idea of a function is you get an input and you get out an output, right? So for example, let's say you want to write a function. So you want to see how does the radius change the area of a circle. You would write a function that says something like, hey, the area, which is my output, right? That's what I want to see. Like, what would the area be? That's the kind of data I want. So that would be the output. What is the area as a function of r? And we know it's going to be equal to pi r squared. So basically, r is the input. You put it in the input, you square it, you multiply by pi, that becomes your output. That's a rule. That's all a function is. It's like a rule of how to transform, I guess, in a way, change your input into an output. In this case, I would square the input, multiply by pi, and there, I get my output. And then I get a graph. It's a pretty neat graph. I get a graph that would look something like this, and we call this a quadratic graph. And this tells me that, hey, the area kind of changes, the area grows bigger and bigger as r increases. Now, this is, the idea of a function is really helpful in a lot of ways, right? You can, for example, you can make a function, what is the height, or like, what is the height of my pen after a certain time t, after I drop it, right? I can write h of t, and it would be something like your initial height 10 meters minus, and then you would do some physics and figure out it would be 4.9, and then the units would be meters. I think meters. Wait, no. Yeah, meters per second squared. What am I doing? Obviously, duh. You would get it would be 4.9 meters per second squared times t squared. This is a function, right? This gives me an output height for some input time. And that's the whole idea of a function. However, when we've dealt with these kind of functions, they've always been limited to one variable, right? Like time is the variable that's changing. I call it my independent variable, and my dependent variable h depends on time, right? But in reality, in the case like something like height, right, depends on a couple of things, right? This right here, this 4.9, it's a constant, but really this is going to, when you do the physics, it's going to end up being 1/2 a, right? It's 1/2 your acceleration, and this is also kind of its own, constant, but this could also be a variable. I'm gonna treat this as a constant though, just because I don't want to deal with too many variables here. But really, a better kind of way to represent this would be, what is the height of my pen as a function of the acceleration and the time? Height really depends on those two things. If I go to the moon, after a certain time t, my pen would be at a different height, right? Like it wouldn't be the same as on Earth, where this constant was 4.9, right? It depends on two different things. I call this a function of several variables, a multivariable function. And you can, this is kind of a physics example, but in a more in a way that you probably better understand, or not better understand, but in a way an example you experience day to day is perceived air temperature. So this is from my book, but not my book, the Stewart book, but perceived air temperature obviously depends on the actual temperature, right? If it's hot, you're going to imagine that the perceived air temperature will be hotter, but it also depends on humidity, right? It's in terms of percentage, I think it's like maybe percentage of the air that's moisture. I don't know, 60% seems like a lot, but it depends on the humidity as well, right? If it's more humid, you can imagine it's probably going to be more hot than it really is. So perceived air temperature, the I think it's like a temperature humidity index or something like that. Perceived air temperature I is going to equal a function of the temperature and the humidity. So you can see this requires two inputs, right? If my input is 90 and my output is 60, if my first input temperature is 90 and my second input is 60, then my thing will be 100. That will be the perceived air temperature. If it's 100 is my first input and 30 is my second input, I can see 104 will be my output. So it's an output that depends on two things. If I just say, hey, the input is 90, I don't know what temperature it could be. It could be any of these temperatures. I need the second input to actually decide it. In the same way that, hey, if I know the acceleration, but I don't know the time, well, there could be all sorts of heights that the pen's at. I need to know both those pieces of information. And now you can kind of make this into a one variable function. I can say that, hey, well, think about f of, so for this example, think about f of 100h. Now 100 is sort of like a constant, right? For this function right here, I know the temperature is going to be 100. I'm only worried about how does the h variable change, right? How does the humidity change? So now I can see that, okay, when my temperature is for sure 100, I get this two-dimensional, I guess I shouldn't think of it in dimensions. You get a single variable function where it's like, hey, 100, f of 100h, right? 100 is the temperature, and then these are the possible perceived air temperatures depending on the humidity. So if you were to compare this function, f of 100h, versus something like f of 80h, these are two different functions, because you can see for f of 80, as the humidity increases by 10%, it's only increasing by 1. Basically, it's only increasing by 1. Here it increases by 2. But for example, f of 100h, every 10% it increases by 5 here, and then 6, and then 10. So you can see, if you were to hold temperature constant at 100, the humidity has a greater impact than if you were to hold the temperature constant at 80. So hopefully that idea makes sense. Now, you can graph these kinds of functions, multivariable functions. And that's the whole reason we even have the 3D plane to begin with, right? Because now, with my 3D plane, I have an x variable, I have a y variable, and I have a third variable. Well, that's perfect because I'm dealing with three variables here. I'm dealing with the two inputs and my output. So I can say, hey, my input can be x, like t is x, and then I can say y is h, and then I get I over here. And then I can graph it like so. So I can say, hey, when the temperature's 80 and the humidity, I can kind of create a graph here, and I create, so this is when the temperature is 80, and then when the temperature is 85, I can graph it. I can graph it just like how I would graph any kind of point, where I just go 80, like for example, 80, 20, and then I go 77. So I don't know why I drew it here. It should be more up here. But yeah, I can get 80 degrees Fahrenheit, 20% humidity, and then I can go up here, and this will be 77 degrees Fahrenheit, I guess, right? That's the perceived air temperature. So, you could graph all the points. I don't know if you'd get like a nice shape, but if you did create a function, and this is a notation, by the way, hopefully you've noticed it's like x and y. So I can say, hey, f of x and y is going to equal, let's say it equals x squared plus y squared. Right? This is a function that takes in two inputs, and then my output is my z variable. So if I were to graph this, hopefully you're familiar, right? This is actually a paraboloid. So I would get a paraboloid sort of like that. One way we can some 3D functions are going to be really crazy, right? I would, for example, I'm not even going to be able to graph this off the top of my head. I can maybe, I'll show you the level curve. I think I can maybe graph this. Okay, f of xy equals, actually no, before we get into that example, I guess I should talk about it first. What we can do to graph 3D functions 3D functions or multivariable functions is use level curves. So level curves are a way, so let me just get this back into my xy plane, but the idea of level curves are like, hey, right here, right? This is when z is equal to 1, z is equal to 2, z is equal to 3. So think about the xy plane. Think about if I were to take at z equals 1, right? So I guess I can draw it dotted. But this circle right here, the circle that I just drew right over here, these represents all points at z equals 1, right? This right here, I can draw the same circle, or not the same circle, but I can draw a circle which represents all points at z equals 2. And then this circle right here, this top one, and then obviously the curve would extend, but this is all points at z equals 3. So I can graph what I call level curves on an xy grid. So yx, and then I can draw a circle like so, and this circle can represent all the points on my surface, x squared plus y squared equals f of xy, all the points that are at z equals 1. And then I can do the same thing, all the points that are at z equals 2, right? And then I can do the same thing. These are all the points at z equals 3. This is called level curves. And this kind of tells us, hey, what points on the xy plane in a way would give me, what points on the xy plane would give me a z value 1, 2, 3. And you know, you can even figure out that, hey, for when z is equal to 1, this would just be like a circle with radius 1, right? Because when I put 1 here, right, because these are just outputs. So if I put 1 here, it's like, oh, it's a radius of 1. If I put 2 here, like z equals 2, it's a radius with root 2, and then becomes like a radius with root 3, so on and so forth. So that's level curves. It's just like a topological map. If you've ever, you know, I've never been hiking, which, you know, because I'm a nerd, I guess. But if you've seen like mountains before, if you've seen a map of mountains, in order to get a gauge of elevation, they make topological maps. That I'll even just show you my book for this, because they have a good picture. Yeah, they have topological maps just like that. And these maps, each line represents the same, a different elevation, right? So, oh my God, my camera got messed up. Oh, this is bad. All right. It represents different elevations. So it's like all points along this curve represents elevation or height, right, at z equals 3. And you will notice the closer that the lines are together, that's when it gets steeper, right? Think about it, because if this is z equals 2, and then this is z equals 3, and then I have z, let's say I have z equals 4, like right very close to z equals 3. So this is my z equals 4 curve that I'm drawing in right now. I know this right here is very steep on my curve, and which makes sense because in our surface, you know, it gets very steep here. And the reason is like, well, from z equals 1 to 2, it's like your x and y has to change a lot. But then from z equals 2 to 3, it's the same increase, but your x and y barely changes. And then from z3 to 4, same increase, but your x and y barely changes. And it makes sense, right? It's like from z equals 1 to 2, my x has to change that much, but from z equals 2 to 3, x doesn't change as much, and then 4 would be right here, and you could see, yeah, it would barely, you know, the x and y points would barely have to change to go up that one. So the closer together they are, the steeper the curve really is. So this would make sense for paraboloid, right? Because as you keep going, you know, for greater x and y values, the surface itself gets steeper and steeper. But for something like a cone, I would expect a level surface, something more like this, where they're all equidistant, right? So like a cone's steepness never changes, so the space between each level won't change. Yeah, the level curves are really good for drawing sketches of graphs. So let me think, let me find an example that I can do really quickly. Is there a good, let me find one. Okay, cool. This is good. So for something, let's say I wanted to draw the level curve, or let's say I'm given the level curve, sorry. So I'm given the level curve, and it looks something like this. So I have my XY grid. God, these markers are dying. Okay, XY grid. And I have, it's like a bunch of parabolas. So I have a bunch of these, my level curve is really all of these parabolas that are really the same parabola, just shifted up and down. And they, they start like right here. I'm just looking at the book for this, but right here, this would be z equals 8, and then maybe this is z equals 6, and then z equals 4, z equals 2, and maybe this is like z equals 1. What would my 3D graph look like? Well, if I were to graph this out on a 3D scale, I know it's going to be parabolas, and I know like, hey, okay, I guess I'm going to have to do something more like this. This is negative x, negative y. But x, y, z. But right here, when the z value is 8, first of all, I know this section is going to be very steep, but when my z value is 8, I get a parabola that's kind of in the negative y, and then is, going out like so, and then it's very steep, and then it becomes very shallow. So I know I can actually expect it to look something like this. And it's going to maintain this kind of parabolic shape. So it's going to actually look something like this. But it's very steep here, and it's the same parabola, but it gets shallower and shallower. So that's how I can kind of use the level curve to figure out like, oh, what will my curve sort of look like? I can use the level curve to kind of maybe not draw a perfect picture, but at least get an idea what it's going to look like. I know it's going to be very steep here, it's going to be very shallow here, and it's going from z equals 8 very high up to something more lower, like z equals 1. So yeah, this has been functions of several variables. Not a crazy idea, I don't think so. It's more so what can you do with several function variables. I think that's what's going to be kind of cool, kind of crazy, but nonetheless fun, I guess. So yeah, thank you for watching. Also, I know I wear this shirt like all the time. Sue me. I like science.